Sorry that you didn't have more time to digest this before the lab exam, but that's why if anybody has any questions today, let me know and I can answer any questions about the lab exams or the labs or whatever. Okay. So yes, they are, yes. So yeah, in this class, just everything is cumulative. The quizzes, um, so go back and remember to refresh your memory about old stuff. Yes, yes. Okay, so any question like this, and it's pretty common that I'll put questions like this on these lab exams. This is the one where you had a curve like this. And it asks you a bunch of questions. Where is it moving in the positive direction, negative direction, speeding up, slowing down, acceleration, positive, negative. Here's how I would always go about these. This is what I would do before you even read what the questions are. I would first, okay, so the endpoints are going to be important. Mark those. And next, the second step is mark all the places where the velocity changes from positive to negative or vice versa. So that's all the places where it's horizontal, where the tangent line is horizontal. So that's here, here, and here. And a lot of people did that, but didn't do this next step. So the next step is you have to identify the places where it changes from concave up to concave down, or vice versa. Those are the places where the acceleration is zero. So if you think of it as sort of like it's concave down all the way until somewhere in here, then it switches to concave up. So I'm going to mark a point here. And as I'm grading this, I mean, you could mark it here or here. I'm not specific about that, but it needs to be in here somewhere. And then it changes from concave up to concave down somewhere over here. So that's two more points that you have to mark. So let's say there, and then I'm gonna, label these all A, B, C, D, E, F, G. Okay. And now in each one of these intervals between those marked points, figure out whether the velocity is positive or negative and the acceleration is positive or negative. So all the way from A to B, velocity is positive and it's concave down, so acceleration is negative. From B to C, we have negative velocity, negative acceleration. C to D, negative velocity, positive acceleration. D to E, positive velocity, positive acceleration. E to F, positive velocity, negative acceleration, because now it's concave down again. And F to G, that's a negative velocity and a negative acceleration. And once you've done that, you can just kind of read the answers off of it. It's moving in the positive direction when velocity is positive. So here, here, and here. The acceleration, when's it positive, from here to here. Speeding up and slowing down, it's speeding up if the signs of velocity and acceleration are the same, slowing down if they're opposite. So speeding up here, here, and here. So that's how I would always go about those. Anybody have any questions about that one? So like normally on, questions, I would say, read the question carefully, think about when you see problems like this, you don't have to think about the question carefully. You do all this stuff and then just look for what it asks you, and you basically have it all written right here in front of you. You can do that on any position versus time graph. So, like for example, what about a graph like this? So mark the two endpoints, mark where the velocity is equal to 0. So this is the only place where it switches, in this case, from negative to positive. And then it changes from concave up to concave down right around here somewhere. And so this is a negative velocity, positive acceleration, positive velocity, positive acceleration, positive velocity, negative acceleration. And so it's moving in the positive direction from B to D, negative direction from A to B, speeding up from B to C, slowing down from A to B and C to D. Okay, I would just, and I'm being a little, maybe going through this a little too quick. Remember what this is not the path that the object is traveling along. This is a position versus time graph. What that picture is makes a big difference in how you interpret it. This case too. Any other questions about the test? Okay. So the last topic that we discussed, we started the last time. We started talking about two-dimensional kinetics. And remember, kinetics means that we're combining what we know about describing the motion, combining kinematics, the stuff we've been doing up until now, with causes of the motion. And those causes, for now, are just force, vectors, and mass. And we came up with the most important equation in this class, Newton's second law. And Newton's second law says if you add up all the forces acting on your chosen object, that's equal to the mass of the chosen object times the acceleration vector of the chosen object. Okay, so F net is the sum of the force vectors acting on the chosen object. M is the mass of the chosen object. And A is the acceleration vector of the chosen object and it turns out the different points on an object can have different accelerations if the thing is rotating. And so the point that we're concerned with is the object's center of mass. Center of mass. And since mass is always positive, the direction of the net force is always the same as the direction of the acceleration of the center of mass. You can see from the definitions of all these things in Newton's second law that this idea of being very clear to ourselves about our chosen object, what is our chosen object, and what's considered the surroundings of the chosen object is going to be really important. Okay, all of this stuff we have to be very clear to ourselves about what we're isolating from the rest of the world. So to be clear, and mostly this is to yourself, but I guess also when you're communicating it to other people. So to be clear about a boundary between the chosen object and the surroundings, that's everything except the chosen object. We'll draw a free body diagram for every use of Newton's second law. And I'm going to take off, I mean, not a ton of points, but I'll always take off points if you use naked second law. Newton's second law without drawing a free body diagram. And a lot of people don't like that because they're like, well, I did it. I got the right answer and you took off points. So really, I do this as a way of building good habits because when you do complicated problems, a free body diagram helps a ton. When you do simple problems, it's pretty easy to get away without doing a free body diagram. And so you don't really see what the big deal is, but I'm just trying to set you up for the point where we do more complicated problems. And by the time we get there, I want you to have the habits, you know. That's sort of my policy on that. But so the next thing we have to talk about is what is a free body diagram? How do you draw it? What are the rules? That kind of thing. So free body diagrams. I'm going to write that a lot, so I'll abbreviate it. Okay, so we're going to draw one of these for every time we use Newton's second law. And here are the steps to follow to draw a free body diagram. First, draw a closed outline of the chosen object with no internal details and no outside objects. Okay, so for example, so let's say that we want a free body diagram of the man standing on the scale. Ooh, something's wrong with his back today. Okay, so if you want to draw a free body, so if the chosen object is the man, then a closed outline with no internal details is just that. Not this, because it's not a closed outline. We want to, what we want, like the key thing that we want in this picture is a depiction of the boundary between the chosen object and the surroundings. And so a drawing of his skin is basically what you're doing. This isn't making it clear what the boundary is. There's no defined inside and outside of that picture, so don't do it like that. Another one is don't do it like that. Partly because that doesn't look like him, but also because the facial features and the arms, we don't care about what's happening inside the boundary. We only care where that boundary is. So no internal details. And then not that either, because the scale and the ground are outside the boundary. We don't want those in there. That is the free in free body diagram. What it's referring to is that the free body is you take your chosen object and you remove it, you make it free from its surroundings. Okay, we're going to represent its surroundings only as the forces that the surroundings apply to it. Okay, so don't do those. We just want a picture of the boundary between the object and the surroundings. Yeah, that's okay with me. There will be times where you'll want more detail than that, but that won't come up for a while. If it's a well, here's the basic ideas. Like if you're isolating a man and say he's holding a cane, then you want the outline to be detailed enough that you can see where the cane is touching his body. If it's just a case like this where it's a man standing on the ground, the only contact is where his feet touch the ground, then a box or a circle is fine. So I think it'll sort of be clear as you go when you need a lot of detail and when you don't. So that's the first step. And then the second step is draw a downward arrow from the center of the object. And label it with the numeric weight if you know what that is. Or if you don't know it or you're too lazy to calculate it, right here, you can label it with mg. That just represents the weight. That's the mass times 9.81. So for the man, draw an arrow down like that, and you can label it. So I think in the example I did before with the man, the mass was 100 kilograms. So 100 kilograms times 9.81 is 981 newtons. Or you can just write it in as mg. Either one of those two is fine. But that's to make sure that you include the weight in your free body diagram. Right now, since everything we're dealing with is still particles, we don't care where forces are applied because objects only exist at a single point anyways. But when we start talking about things as rigid bodies, where we do care about the length of the object and we do care about where on the object forces are applied, the weight force we're always going to treat as acting exactly at the center of mass of the object. So that's like if you did a measurement of where if you acted like the weight was a single force acting at a point in your body and did the calculations required to figure out where that single force would have to act, it acts at your center of mass, somewhere in your torso, above your belly button or whatever. And then step 3. So anybody remember I broke down all the forces acting on objects in this class into 2 types. The first one was the weight, and the second one is everything else. What did I call that type of force? Everything else, that's sort of getting at it. Everything else is a contact force where the surroundings are in contact with the boundary of the object. So the third and last step is at each place where the surroundings make contact with the boundary, draw an arrow in the direction of that contact force. And label that vector with either a numeric value if you know it or a variable. So I'll say with a value or a variable representing that value. So for the man on the scale, there's the outline. We have the downward force of 981 newtons. Where are the surroundings in contact with the boundary? Only the scale touching the feet. There's also air molecules touching his skin, but just like in free fall, we've always ignored that, and we're mainly going to always ignore that unless it says something specific about a wind and how much force it applies or something. The scale, and this is the next thing we're going to talk about, is how to know what direction certain contact forces are acting in. But the scale is pushing up from the ground onto the person's feet. So the direction of that force is like that. And we don't know at first glance what the magnitude of that force is. So we'll just label it with a variable. And I'm going to call it capital N for normal force. And by the way, I'm going to use this a lot. That capital N stands for normal force. And in this application, normal doesn't mean usual or common or whatever. It means perpendicular. So that force N is a force that's perpendicular to the ground in this case. Okay, perpendicular to the surface that's applying that force. Okay, so that's it. That's how you do a free body diagram. The next thing we have to do is we have to learn about what directions different forces act. So next we have to talk about the directions of contact forces. And there are three types that we're going to deal with. The first one is pushing contact along a flat surface. The second one is a pulling contact. Um, and these are all, pulling contact is always a force where the contact between objects could be replaced with a cable. Okay, so right now I'm pushing down on the table. So if I moved just a little tiny amount of distance between my hand and the table, just move my hand up a little bit, would the same thing work if I replaced that with like a string or something? No, because I just push the string flat, you know, and the string wouldn't apply any force at all. Okay. But now if I'm pulling up like this, could I replace a little bit of, you know, so let me do it like this. So pulling up on this. Could I replace the contact with my fingers with a little string? Yeah, string can do that. So this is pulling. This is not pulling. This is pushing. And then the third type is friction force. And friction force happens when an object is sliding along a surface. Okay, so the first one we're going to get into is pushing contact along a flat surface. Um, and as an example, let's think about this case. This is going to be the first problem I'm going to do involving pushing. So let's say that we have one card over here with a mass of 10 kilograms, and it's in contact with the ground. And then it's also pushing against another cart. Let's say this one has a mass of 20 kilograms. And then let's say that there's a force, and we don't always know where the forces come from, but let's say that there's a 30 Newton force applied to the right side of the 20 kilogram cart. Okay, so where is pushing contact along a flat surface occurring? In this case, it's occurring in three spots. Well, three spots if you consider that we're dealing with these as particles, and so we're not making a distinction between the two wheels of each, or I guess it's really four wheels if you think of it as three-dimensional. We're not making a distinction between these 2 points of contact or these 2 points of contact. We're just thinking of this as the ground is pushing against the wheels, and the wheels are pushing down against the ground. So there are three spots where this pushing is occurring. Here, here, and here. And how do you know that all of those are pushing? Imagine lifting this upper millimeter and squeezing a tiny little string in there. Did that string transfer the same force that those wheels are? No, crumble strings don't do that. And so that's pushing, same thing. And it's also not sliding, which, we'll talk about friction last. But anytime you have wheels shown, that's meant to indicate that we're ignoring any friction. Here, same thing. Could you put a little string in between those two and transfer that force with the string? No, string would compress, so pushing. Yes.
So what is the chosen object?
We haven't chosen anything yet. But what we're going to do when we do start calculating stuff is I'll do it choosing the 10 kilogram and do some calculations, and then I'll do it separately choosing. I think first I'll do it with the chosen object being both of them together. Then I'll do one, then I'll do the other one. We'll just see what we can figure out from all these different ways of thinking about it. Yeah, exactly. Yep. Yeah, so I mean, what you choose as your, what you pick as your chosen body is like going to be a crucial thing in doing these problems. Okay, so when two objects push against each other, um, the contact force is always perpendicular to the boundary between them. That's what I'm always calling the flat surface in pushing contact along a flat surface. And it's always toward the chosen body, away from the contacting body. Okay, so yeah, we're not really going to think about it that way yet, but there is. Okay, well, I'm going to go through an example. Okay, so let's do this example above. So we have, okay, so we have the 10 kilogram, the 20 kilogram, and we have a 30 Newton force this way. And we want to first calculate the acceleration of these two. And here, you can imagine if these two things are rigid and you apply a force to the right side of the 20 kilogram box, they're going to accelerate the same. They're going to just move as a single unit. So calculate the acceleration vector of the carts. And then B, we want to calculate the force vector that's applied to the 10 kilogram cart by the 20 kilogram cart. And then the last thing we want to do is calculate the force vector applied to the 20 kilogram cart by the 10 kilogram cart. And we're going to notice anything. Not yet, we haven't done it. But I'm going to point out something that maybe some of you could guess, but it's going to be a key thing in this class. Not quite yet, but in a week or so. Okay, so let's do this. Okay, so, well, anybody have any questions about the problem? All right, so to calculate the acceleration, and this is always going to be the case, if we want to calculate the acceleration of these two carts together, our chosen object for part A is going to be both of the carts together. We're going to treat them as a single unit. And your first thought might be like, are you sure that's allowed? But remember that, like, this 10 kilogram cart, I mean, we only think of it as a single thing because a cart is something that someone named, you know. But remember that it's really made up of like atoms and molecules and wheels and all sorts of different stuff. There's really nothing making this a thing, you know what I mean? And so, yeah, we can isolate this. If we wanted, we could just isolate a wheel. We could isolate those two together. We could isolate those two as part of the earth. We get to choose where we make our boundary. Okay, and we're going to make our boundary around. So let me draw it. So we're going to isolate both carts together. Let's see. Okay, so here's a free body diagram of both carts. And I'm going to do sort of a detailed outline just so you can tell what I'm talking about, but you don't have to do it with this much detail. But okay, there's the outline of the system that we're isolating. So that's step one of drawing a free body diagram. Step two is to draw a force down from the center of the object and label it with either the weight of the object numerically or with mg. What's the mass of our chosen object? Yeah, 30 kilograms, because we're just adding both of them up. So 30 times 9.81 is the weight. And if you calculate that, you get 294.3. And now that we've dealt with the weight, we're just going to go, I'm used to going counterclockwise. It doesn't matter which way you go, but you need to mentally go all the way around the outline and think about where the outside world, the surroundings, are touching the object. The first place is over here, the force that's applied to the boundary. So first thing we have to do, this first because that's where I'm starting, is apply that 30 Newton force there. Okay. And now keep going around the boundary. There's no contact until you get to the wheels over here. And there's a contact at each one of these wheels, a contact at each one of these wheels. I'm going to lump all that in since we're thinking of this as occurring at a single point. I'm going to call all of that the total normal force, or the total pushing contact applied to the wheels by the ground. Okay, so I'm only going to draw it in one place. And how do I know what direction it goes? It's perpendicular to the flat surface, and the flat surface is the ground. And it's toward the chosen body, away from the contacting body. So we know it's perpendicular to the ground, so it's up or down. And then we know it has to be up because it's toward the wheels, away from the ground. And the label I'm giving it is that capital N for normal force. Anybody have any questions about that? Yes, that's right. Yep. So now we've drawn the free body diagram. Now we can write Newton's second law. And let's say we're using a coordinate system like this. So that normal force is in the positive y direction. So in component form, that's 0n. The weight force is in the negative y direction. So in components, that's 0, negative 294.3. And then the 30 Newton force is in the negative x direction. And so in components, that's negative 30, 0. So now I've put in every force vector that shows up on the free body diagram. And all of this together adds up to, so that's our F net. Okay, the sum of those forces is our F net in Newton's second law. And then the right side of Newton's second law says that's equal to the mass of the chosen object. So what's that? 30 times the acceleration vector of the chosen object. And we could say we don't know anything about the acceleration, but think about how this thing will move. This is an idea we're going to use all the time on systems that roll or slide. We're going to assume that this system isn't going to sink into the ground or jump up off the ground. All of its motion is going to be horizontal. Okay, it's going to be horizontal. And we don't have to decide whether it's going to be in the negative x direction or the positive x direction. All we're going to do is we're going to say it's going to have an x component of acceleration, possibly, but we know it's not going to have a y component of acceleration. Okay, so we're going to treat that acceleration as something in the x direction, and we don't know what. So that's why I'm calling that a, and then 0 in the y. So this thing here is our acceleration vector. This is the mass of the chosen object. And now we have two equations, an x equation and a y equation. The x equation, what does it say? So 0 plus 0 minus 30 is equal to, what do you get on the right side? 30a, yep. And now that's just an algebraic equation that we can use to solve for a. So negative 30 is equal to 30a, or in other words, a is equal to negative 1, and since this is SI units, that's meters per second squared. And then there's a y equation too. That's not going to give us anything that we're looking for, so I'm not going to solve it. But what this says is, so read off what the y equation says here. N, yep. That's right. Yep. Right. Yep, exactly. And so we could use this to solve algebraically for n if we were asked for it or needed it for something. But now, what can we do with this a? What we were asked for is the acceleration vector. notice that this is the acceleration vector. We just didn't know yet what A was. Now that we know what A is, we can plug it in here to get the acceleration vector. So from the X equation, the acceleration vector is equal to, plug -1 in for A. The Y component 0. So you can write it like that. Or you can also write it, another way to write the vector is give the magnitude and the direction. It's in the negative X direction with a magnitude of 1. So you could write it as an arrow that way with a magnitude of 1 meter per second squared. Those are equivalent. Yes? Right. That's right. That's a good question. We don't have enough information to know that. Like you can imagine imagine that box being a wagon and like a 50-pound kid is sitting right over one of the axles. There's going to be more force there than there is on the other one. You know what I mean? And so yeah, we need more information. If there's no, I'll just leave it there for now. Okay, so now we know the acceleration vector. And notice that acceleration vector is true for each individual cart also. Okay, so like look at this picture. We calculated that if you treat this as a single object, and a single object is accelerating that way at 1 meter per second squared. We could also say that, so now if we isolate the 10 kilogram cart, we know that the acceleration of that one is 1 meter per second squared that way. And if we isolate the 20, we know it's accelerating that way at 1 meter per second squared. So now that's what we're going to use when we isolate those two individual ones. And this also is a technique that's going to be important in a lot of problems. If you need to calculate the acceleration, first isolate everything together. Then you can use that acceleration you calculated when you isolate the individual ones. Any other questions before I start isolating these individual carts? Okay, so now for part B, we're trying to calculate the force on the 10 by the 20. So I'm going to isolate the 10 kilogram cart and see what forces are applied. And the first thing I have to do is draw a free body diagram of the 10. There's the outline. The second thing we do is draw a downward weight force, and that's equal to the mass. What's the mass of our chosen object? 10 kilograms. 10 times 9.81 is 98.1 newtons. At the wheels, there's an upward pushing force from the ground. Is that the same as the N that we had before? No, almost certainly not, because that N from before was also including the force that the ground was applying to the 20 kilogram. So I'm going to call this one N10, N sub 10, just to make a distinction between it and the other one. And I'm going to keep going around the boundary. And again, this N10 is really distributed over all the wheels, but I'm treating it as a single one. Where's the other place that the surroundings touch the boundary? There's only one more place. Yeah, right here, there's contact between the 10 kilogram and the 20. And that's a pushing contact along this flat surface. So it's either to the left or the right. That's what the rules are for a pushing contact. Left or the right. It's toward the chosen body, away from the 20. So it has to be to the left. Left. So we have a force this way. We don't know what the magnitude of that is, so I'm going to call it R for reaction force. And now we're done, but that is a little surprising to a lot of people, I think, probably. That's a complete free body diagram. But I think a lot of people's natural reaction is like, well, what about that 30 Newton force? Because like, where would this cart go if you didn't apply the 30 Newton force over here? It would just sit there, you know? So how could this move without it feeling that 30 Newton force somehow? Okay. Well, there's two answers to that. The first one is just be disciplined about following the steps, and you'll always get these right. Okay. So the steps just say there's the weight force. Now we go around the boundary and look for contact. Anything that's not contacting the boundary, we skip. Okay. And that'll always give you the right answer. But like the intuitive answer is that when you push on that 30, when you push on the 20 Newton cart with that 30 Newton force, that has the effect of increasing how much the 20 is pushing on this. So indirectly, that 30 Newton force is felt by this, but it's felt through this reaction force. Okay. It's not directly 30 Newtons applied there. Anybody have any questions about that? We know the acceleration, right? Yep. That's right. Yep. Okay, so now we'll go to Newton's second law. The weight force is in the negative y direction. So 0, negative 98.1. The normal force is in the positive y direction, so 0, positive n10. The reaction force R is in the negative x direction, so that's negative R0. And now those are all the forces applied. What are the units for all those? I'm not writing units in this, but what are the units there? Each one of those is newtons because we're in SI units and all of those are forces. Yeah, that's true. But the right side is Newton's law too, and those aren't newtons. And then Newton's second law says those are equal to the mass, 10 kilograms, times the acceleration. What's the acceleration? That's what we solved in part 1. Negative 1 for the x component, 0 for the y component. Yep. Because both of those two are moving as a single unit. And so whatever is the acceleration for both of them is the acceleration for the individual ones too. That's going to be something we'll use in a lot of problems. That wouldn't be true if there was like some kind of flexible contact between the two of them. Like if there was a spring connecting them, you'd have to be careful with that. But if they're rigid, then yeah, that's how it works. Okay, so this gives us two equations. The x equation says 0 plus 0 plus negative r is equal to negative 10. Solve that algebraically for r, and it just says that r is equal to 10 newtons. the y equation doesn't give us anything that we're looking for in this problem, but it says negative 98.1 plus n10 is equal to 0. And now notice that this vector here is the force on the 10 kilogram by the 20 kilogram. That is the force. We just didn't know what R was yet. Now algebraically we solve for R. So now we just take this value and plug it back in there, and that gives the force vector. So the force on the 10 by the 20 is negative 10, 0 newtons. And what direction is that acting in the coordinate system? It's in the negative x direction, pointing to the left. So you could also write this as an arrow pointing to the left with a magnitude of 10 newtons. Those mean the same thing. Any questions about that? Okay, so now we're going to isolate the 20 kilogram, and we're going to calculate the force applied to the 20 kilogram by the 10. Anybody have an idea what that answer is going to be? What's the force on the 20 by the 10? It is going to be the same. It's going to be 10 newtons just acting in the opposite direction. And that's getting at something that's going to be a key thing for us called Newton's third law. That says, I think the way it's written is something like, for every action, there's an equal and opposite reaction. It's really something in Latin. But and what that means is that whenever two objects are in contact with each other, they, no matter what the situation is, they're applying forces of the same magnitude to each other in opposite directions. We'll talk about that in detail because that's sort of a confusing, intuitive idea in a lot of cases. But so what we expect to have happen when we isolate the 20 kilogram cart is we're going to calculate the force on the 20 by the 10 to be equal to positive 10, 0, or 10 newtons pointing in the positive x direction. Okay, so here's the 20 kilogram cart. That's the outline. And there's a downward weight force that's equal to 20 times 9.81, so 196.2. And now we'll go around the boundary looking for contact. So let's start over here. There's a force applied to the boundary here. What's that? That's the 30. And then nothing, 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 nothing until we get here. What's the force applied there? We're assuming we don't know the magnitude, but yeah, that's a pushing contact because you couldn't put a string in there and expect the string to apply the force. And so it's perpendicular to the surface, so it's either left or right, and it's toward our chosen body, away from the contacting body. So in this time, it's pointing to the right. Okay. And for now, I'm going to say we don't know what that is. I'm going to call it R again because it's going to end up giving us 10 just like the last one did. And then there's a pushing contact from the ground to the wheels. I'll call that N20. And now Newton's second law. So there's this R force in the positive X direction. So that's R0. N20 is in the positive Y direction. So that's 0, N20. The downward force of 196.2, so 0, negative 196.2. Then there's the 30 Newton force going to the left. That's the negative X direction, so that's negative 30, 0. That's our F net, and then that's equal to the mass of the chosen object times the acceleration vector. What's the acceleration vector? Yeah, negative 1, 0 still. So we have an X equation that says R plus 0 minus 30 is equal to negative 20. And if you solve that for R, you get, so add 30 to both sides, and you get R is equal to 10 newtons. You also get a Y equation that we're not going to use, 0 plus N20 minus 196.2 is equal to 0. But what we really want to use is this R value because this is our force on the 20 by the 10. That's what we're looking for. We just needed to get this R value so we could fill it in. And so now substitute 10 in for R, and you get that the force on the 20 by the 10 is equal to 10, 0. Or in the positive X direction with a magnitude of 10. So we can think of that as an arrow going this way with a magnitude of 10 newtons. So what we got in this one case is that the force on the 10 by the 20 was equal and opposite to the force on the 20 by the 10. It turns out that that's a general rule. But we just saw it in our specific case. We calculated it. And it's cool how that works out. I think when you first see it, it's like, how did, when we isolated the 10 kilogram cart, somehow it knew that 30 Newton force was there, even though it doesn't show up in the math at all. And then we went to the 20 and the 30 Newton force was there, and in both cases we get the same thing. Well, in essence, like the way it works is that when we isolated the 10 kilogram cart, what we put in here, we did know about that 30 Newton force because we used the 30 Newton force in part A to calculate the acceleration. Okay. And so it does get in there indirectly, but to follow the steps, all you do is apply the weight force, go around the boundary and apply the contact forces. Yep. Yeah, so in problems like this, you always have to calculate the acceleration first. That's what you want to do first. And to do that, you want to isolate the whole system together. Yep. Any other questions? Okay, let's stop there. I'll give you a couple of free body diagram problems to work on. A what? Which one? The last, this one, yes. Thank you.
Quick question.
Yep.
I'm curious to know